The amazing physics of Perseverance and EDL. After almost 7 months of interplanetary travel to Mars, the Perseverance lander has to transition from an interplanetary projectile traveling at over 40 kilometers per second relative to its launch point, the point in Earth's orbit where the vehicle left on its way to Mars, to a functioning science lab and mobile outpost on the surface of Mars. In doing so, the technology aboard the vehicle and the rover, some new and some already developed, needs to perform flawlessly the first time, otherwise it's game over. Some amazing physics takes place in the execution of the mission, from choosing the launch date and window, the launch window, the orbit and trajectory of the vehicle, otherwise known as the cruise phase, to the EDL phase, and the mission hasn't even started yet. Welcome friends, this is Dr. Jim Daly of Astronomy for Change here, your host, to bring you along on an amazing adventure in physics, from the launch of Mars2020 Perseverance to the surface of the red planet. The spacecraft consists of multiple interdependent components: the descent stage, the back shell and heat shield, plus the rover. The back shell and heat shield together constitute the aeroshell. The entire mission is a masterpiece of planning, engineering, and choreography, with the mission's launch and cruise as important as the arrival and landing. As there is just so much to cover, this will be the first of 2 videos. How do we get to Mars, or any of the planets for that matter? Aside from using a launch booster with the appropriate power, we also have to consider the orbit of the destination, and in this case that would be Mars. This requires a knowledge of where our destination will be in its orbit when we arrive, and a consideration of the energy requirements to get us there on time and in the right place. The solar system is a big place, so our calculations have to be precise and accurate. And this is where we will begin our discussion on this first video. As we know, the great German mathematician and astronomer Johannes Kepler gave us his 3 laws of orbital motion, and later Isaac Newton gave us his 3 laws of motion, and it is the use of these laws now that will provide the necessary tools to calculate the correct orbit and trajectory of our spacecraft. Yes, we're going to put our spacecraft in orbit, but not just any orbit. To minimize the energy requirements necessary to traverse the huge distances between the planets, distances that are measured in the 100s of millions of kilometers, the German engineer Walter Hormone suggested in 1925 the use of an orbit that takes advantage of the origin and destinations, the 2 principal planets involved, placement, and thus these types of orbits became known as Hormone transfer orbits, and as such are the basis of all interplanetary missions today. Hormone transfer orbits are used to maximize efficiency while minimizing energy expended by taking advantage of orbital dynamics that start with Kepler's and Newton's laws. Before we begin though, we should review the basic properties of an ellipse. We have the semi-major axis, the foci, the periapsis and apoapsis. The periapsis is the closest point to the central principal gravitating mass, and in the case of our solar system, that would be the Sun. The apoapsis, otherwise known as the apogee, would be the furthest distance from that same object. Kepler's laws of orbital motion are universally applicable and apply to all 2-body bound orbits, and all orbits are elliptical. Equal areas are swept out in equal times. The period squared is equal to the semi-major axis cubed. Kepler's first law: all orbits are elliptical. Because of gravity, there are no orbits in nature that are perfectly circular by design, since even the smallest mass will exert some influence or perturbation on a larger mass. This will cause each of the masses in a 2-body system to be off-center and orbit around their barycenter, and we can see in this diagram 2 dissimilar masses, one larger, one smaller, orbiting around their common center. And you can see that they will trace out an elliptical arc. The magnitude of this influence, or how much one changes the other, is known as the orbit's eccentricity, and will always be greater than 0 and less than 1 for elliptical orbits, orbits with a finite period. Parabolic or hyperbolic orbits have indeterminate periods and don't repeat and have eccentricities of 1 or greater. You can see in this example here, in this insert, Pluto with Charon. This is a live video obtained by the New Horizons as it flew past Pluto back in 2015. Kepler's second law: equal areas are swept out in equal times. There is an equivalence between areas swept out by a body in orbit and the time taken to travel the orbital arc. Equal areas in equal areas in equal intervals of time. Kepler's third law: the period squared is equal to the semi-major axis cubed. Since we're discussing Mars, let's use the distance to Mars as an example. Mars is 1.523 astronomical units from the Sun, where an AU, an astronomical unit, is the semi-major axis of the Earth. The distance from the Earth to the Sun is 150 million kilometers. The measured orbital period of Mars is 687 Earth days. Using the simplest form of Kepler's third law, we cube Mars' distance of 1.52 AUs. You can see the calculation in the right-hand column. And then take the square root of that as a result for 687 days. We take that 1.88, multiply that by how many days in our year on Earth, and we arrive at the exact value of 687 days. It's the measured orbital period of Mars. So let's take a look at the Hormone transfer orbits. Regarding Kepler's first law, the first of his laws, we need to consider another property of an ellipse: the periapsis and apoapsis, or the closest and furthest distances of a body in its orbit, respectively. This requirement is the basis for launch windows for all NASA interplanetary missions to date, and, in the case of Mars, this window opens every 26 months. Every 26 months. A Hormone transfer orbit uses the orbital angular momentum of the originating planet, the Earth in this case, to essentially slingshot the launch vehicle using the planet's orbital angular momentum tangential to Earth's orbital path to advantage to be the most energy efficient with a modest cost and travel time. In some cases, Hormone transfer orbits are not the fastest routes, and I should point out at this moment, Kepler's second law, which we looked at previously, this is what some would consider the most expressed form for what's known as the conservation of angular momentum, a principle in physics that basically states that the total angular momentum of a system is a fixed value. So the further away a body is from the central gravitating mass, the slower it's going to move in its orbit. This, combined with a modest boost in tangential velocity in the case of an Earth-Mars Hormone transfer, an additional 2.94 kilometers per second, results in the greatest overall conservation of propellant. In the case of our Perseverance that just landed, the second stage boosted the velocity to 39,600 kilometers per hour, or 11 kilometers per second. This, on the left-hand diagram, you see the yellow ellipse is the new Hormone transfer orbit. It's an actual orbit that's established by the spacecraft. The two other orbits are the principal orbits of the two planets, which are depicted in this diagram as circles. We know from nature there's no such thing as a perfectly circular orbit. This is just for the sake of a diagram to explain the concept. The extra boost in energy, this extra 2.94 kilometers per second, is required. In the case of Perseverance, the second stage boosted the vehicle to a velocity of 39,600 kilometers per hour, or 11 kilometers per second tangential to the Earth's orbital path, with velocity of 29.8 kilometers per second. That's the speed of the Earth is traveling in its orbit around the Sun. So the vehicle launches from the Earth. According to Newton's first law, the vehicle retains that velocity, but we're adding an extra 2.94 kilometers per second plus the 11 kilometers per second tangential which is the escape velocity. So I mentioned previously at the beginning of our video, over 40 kilometers per second cruise velocity as it's leaving the Earth from its launch point on its way into cruise phase. That's the sum of all these velocities. The Earth, the big one is the slingshot velocity it gets from the Earth. Okay, that's Newton's first law, which states that every object in motion tends to remain that way unless acted upon by an exterior force, external force. Or said differently in a more general form, the state of any object will remain unchanged unless acted upon by an external force. Okay, the extra boost in energy is required. The extra 11 kilometers per second is required to escape the Earth's gravitational pull and to provide the extra energy boost as the vehicle moves further out from the Sun towards Mars. We must consider Kepler's second law, as the conservation of angular momentum will cause the vehicle to slow down as it recedes from the Sun on its way to Mars. Without this extra energy boost, Perseverance would never escape Earth's gravity or overtake Mars. Getting back into talk a little bit more about the second law. Equal areas are traced out in equal times, in different terms, in terms that are more germane and apropos. The closer a body is to a central gravitating mass, the faster it will travel in its orbit. This is almost the definition of a physical principle known as the conservation of angular momentum, and will play an important role as we move forward in our discussion. Additionally, and in agreement with Newton's first law, that the state of a system remains unchanged in the absence of an external force, the vehicle will be moving at the tangential velocity of the Earth at the launch point. After launch, the Earth will act, therefore, as a slingshot, imparting a tiny fraction of its orbital angular momentum to the vehicle as it leaves the Earth. This, in addition to the escape velocity of the Earth of 11 kilometers per second. Okay, this generally would be from a parking orbit 300 kilometers or so above the surface. That would be the vehicle's velocity relative to the launch point or the point it departed low Earth orbit. This velocity will immediately begin to bleed off as the vehicle recedes outward away from the Sun towards Mars. Hence the extra kick necessary as it leaves low Earth orbit of 2.94 kilometers per second to put the vehicle in a Hormone transfer orbit. This final velocity is the sum of the escape velocity, 11 kilometers per second, and the tangential velocity of the Earth in its orbit around the Sun of 29.8 kilometers per second, and is approximately 41 kilometers per second relative to the launch point. The point where the Earth is at its periapsis will be where it's moving with the greatest orbital velocity, and thus that will be the point ideally where we want to launch from, but not every 26-month window will allow us to do that. And in the case of Perseverance, that wasn't the case. We arrived at Mars at its apoapsis, at its furthest and thus slowest point in its orbit. As stated before, and according to Newton's first law, we retain the velocity of the Earth at this point in its orbit. This is the first step in putting the vehicle into a Hormone transfer orbit. The next step will be at the other end, at Mars, where Mars will be at its apoapsis point, or its greatest distance from the Sun in its orbit. Some of the animations used in this video were produced using Cosmographia, a mature, open-source, freely available application for all platforms, available from NASA and the Jet Propulsion Laboratory, and the link will be left in the description. Some Mars fun facts. Mars 2020 Perseverance launch and arrival dates. Just shy of 7 months by 2 weeks. Mars acceleration due to gravity is 3.72 meters per second squared compared to Earth's of 9.81 meters per second squared. That means every second an object is falling, Mars' gravitational field is falling an extra 3.72 meters every second. In this case, compared to the Earth's, it's roughly 1/3 of the Earth's gravity. The mass of Mars compared to the mass of the Earth, it's roughly 1/10. In fact, to within a very close tolerance, it's 10% of Earth's mass. Mars' equatorial radius is almost 3,400 kilometers, compared to Earth's is 6,370 kilometers. One Martian day is 24 hours, 37 minutes. roughly 37 minutes longer than ours. This period is known as a sol. Mars' orbital period is 686.98 rounded to 687 Earth days, 1.88 Earth years, and we did that calculation previously. Now, 668.6 Martian sols, or 668.6 periods, 24 hours, 37 minutes long. Okay, and those are the distance to Mars from the Earth at the time of launch and at the time of arrival. Distances to Earth and Mars and to the Sun at the various times are listed here. And the distance to the Sun from Mars at the time of arrival. So you can see that it changed quite a lot in 7 months.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, Please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and choose a membership level suitable for you. Every little bit helps us produce the great content and further our mission. Also, why not consider becoming a member? Choose the membership link here, click it, put your name and your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron helps us grow and improve and more fully realize our mission. Thank you. This is Dr. Jim Daly for Astronomy for Change. Until the next video, please stay well and keep looking up.